So in this video, we will study and discuss about the Haberman data set, and we will do some exploratory data analysis on this and understand few insights which we can get from the analysis. So first of all, let us see the data set. So this data set I have actually got it from Kaggle, and the first column actually is the age column. The second column is for the year. The year is actually 19. It is the last two digit of the 1900. So the year is such as 1964, 1962, 1965, 1959, and so on. This is about the this is about the data set, and here you don't have any columns written, so you have to actually get to the data dictionary. You can easily get the data dictionary when you actually search. You have a website apart from Kaggle also. If you search Haberman dataset dictionary, so you can get various kind of dictionaries available. So to actually simplify the process, I have actually written here the first column is age, the age of the patient at the time of operation. Second is the year, so year in which the patient had an operation in the 90s. If 64 is written, it means 1964. Third is the nodes. Nodes here are the number of positive axillary nodes detected. So I am not a domain expert, but if somebody have a domain knowledge about this, they can know that the auxiliary lymph nodes has a function to filter fluids before they are eventually released into the bloodstream. And having a cancer cells in the nodes tells us that the cancer might have spread to other body parts also. So number of the more number of positive axillary nodes you will detect, the kind of probability of getting the cancer will be increased. But again, it has a distribution, like you have some range. Suppose a range of like 4 to 10 positive auxiliary nodes actually can give you the more probable cancerous cells in your body, rather than if it goes further ahead. So you can also actually search here if you want, like yeah, 1 second, there was some lag. So positive auxiliary lymph nodes. I would recommend whenever you get a data set, actually there is no internet, let me check once. Searched positive auxiliary lymph nodes. Here you can see that what do positive lymph node mean. So you can actually go and see that what is the auxiliary lymph node, and you can also see lymph node cancerous. So here there is a survey which says that 4 or more auxiliary lymph nodes are cancerous, and inters have meta thing which I don't have a knowledge about. Better data set you can actually go on and you can actually see various kind of feature information which you can get from the Google. So positive lymph nodes are such. There is the target two values, 1 and 2. 1 indicates that the patient survived 5 years if the operation was like after operation, if the patient could survive more than 5 years. If the patient could survive more than 5 years, it has the value 1, and 2 indicates that the patient died with 5 years. Like within 5 years the patient died. So you can say that operation also has the effect. Like if the operation was like highly successful, the patient would survive after 5 years also. But if the operation was not that effective, then you may conclude that the patient died within 5 years. Now this data set contains cases from a study that was conducted between 1958 and 1970 at the University of Chicago's Billings Hospital on the survival of patients who had undergone surgery for breast cancer. This obviously means that whosoever has come for the treatment were having the breast cancer. And as per the breast cancer, everything was noted. What was the age at the time of operation? What was the year in which the patient had an operation? And like how many nodes were detected and what was the survival status. So I have imported all the necessary libraries here. So I have imported NumPy as NP, then Pandas as PD, then for visualization I have used Matplotlib and Seaborn. I have also tried to filter the warnings. Like I don't want any warnings here, and I have like downloaded this Haberman dataset. So I'm reading it. Df is equal to pd.read underscore csv. So let us execute these commands. Also, I know that I do not have any column in my original dataset. Column names, basically, I do not have all these things here. So for that, I have actually made a column. Like I should have age, year, nodes, and survival. The code is df.columns. So this will be added. So let me execute this also. Now you can actually see the head, dataset head. The first 5 rows. So it says age, year, nodes, and survival. 1 or 2. Now you can actually see the value counts of survival, because these 3 are actually the 3 features or 3 independent features, and we have to predict this. So first of all, you have to know the agenda. What is the agenda here? The agenda is not actually to make any random insights. The agenda should be, if I can say, let me put. So what my agenda should be, given a patient with the age, with some age, then maybe the year for operation, the year of operation, and the lymph node detected. Actually, I can say number of lymph node detected, number of lymph nodes detected we have to predict, we have to conclude because we are not making a model, we are just trying to do a exploratory data analysis. So we can say that we have to predict, or most importantly conclude, we have to conclude whether, conclude the chances, conclude the chances whether the patient will live less than 5 years or more than 5 years. This is what our agenda is, to be very precise. Given a patient, and the proper prop scenario. So you just have to consider yourself that suppose you are in a hospital and a patient has come with some particular age at that particular time, and they suppose they have undergone a operation earlier. So if they suppose come and they have said that, okay, my name is David, I am maybe 35 years old, I have had operations 2 months back, and I had like 6 positive lymph nodes which was detected. What do you think? Would I be living less than 5 years or more than 5 years? So given the information of the data set, the previous data, these are actually the data set is the training data. From here you have to train your brain, train yourself to know, make out the patterns, so that you could be able to figure out some patterns and say that, okay, there are 60% chances that you won't live more than 5 years, or it is a 60 or 70% chance that yes, you may live more than 5 years. So such kind of things can be made up, or some such kind of patterns can be found out in an exploratory data analysis, or EDA. Okay, later you can make some models, you can use your logistic regression or ensembles technique, whatever is there, and then also there is a prediction. You can use all your recall, precision, accuracy to find out whether the model is correctly behaving or not. That is a different ball game, but right now just we are on the very level 0 of the project. We just need to give some meaningful insight so that my company or the hospital can actually be okay, maybe this details can be used by the insurance company. If somebody who would have given some medical insurance, who must have taken these information, may be useful for them. So there are n numbers of things which such kind of insights may help people to take various kind of decisions. So keeping this in mind, keeping this goal intact, we are not going to go and randomly do any plots without any unclear understanding. We would just like to keep our goal intact and try to try to figure out what all kind of patterns which we can take here. So before that, let us actually see what is the shape of the data. So the shape is, we have 305 rows and 4 columns. Now the data set is quite small, 305 rows. Okay, so once you get such kind of small data set, you won't be like 100% correct on any of your predictions, first of all, because 305 is a very small number to say that something is truly going to happen. Because if the data set is above like 50,000 or 1 lakh rows, then there might be some chances, something has happened out of 1,000 time only once. That can give you much more confidence. But howsoever, for the educational purposes, we are going to see how we can use this data set to get the patterns. So this is 4 features and these many rows are there. Now let us see whether it contains any null values or not. So we will simply write this is null.sum. When I run this code, I can see that there is no null values here. Okay, null values are okay, but let me see if some duplicates are available here. Maybe there might be some people, because the data is erroneous, maybe it can be duplicated. So let us see. So duplicated dot value counts. When I see that there are 17 rows which are actually the duplicated. These are duplicate rows. But now this is a big question. Whether you should remove the duplicate or not. That is the main question. So let us see the data set first, the head which we have seen. So there is an age, there is a year, there are the nodes and the survival. Suppose I say that let us understand about the first row. The first row says a person was 30 years old while doing the operation in the year 1962, and the 3 nodes were detected, and he survived more than 5 years. I would like to say that I may have 10 other people who are like 30 years of age and going along with this guy. Maybe these are his friends. Another 5 people who would go with him to get operated, and maybe they might have that is a coincidence that they might all get 3 nodes detected. That is not an impossible thing in the situation, in the scenario. It can happen, right? Even if there would have been name, then you would be somewhat confident, then okay, there will be no 10 Davids in like this small data set. But these things are actually you should keep in mind before removing the duplicates. So if I see here, I don't think I should be removing the duplicates as such. I should not practically be removing the duplicates, because I don't know. I don't think it is an impossible task to actually the people who are like having the same kind of age and operation year and number of nodes, and they are surviving at the same thing, can actually make some confusion, or create some doubt that okay, this cannot happen. This can happen. This is very much possible. So we will not remove the duplicates value here. So we should remember that we will not remove. So I'll just write the comment here. We will not remove the duplicates, as these can be a genuine possibility. Okay. So now the next thing. Let us see our information. What is the info? So df.info. However, we all know that it is all integer. It will be all integer type. So non-null integer. This is what we have. Now, I would like you see df dot, if I can see df dot survival dot value counts. When you do that, you would get the value counts for survival. But I don't want 1 and 2. I would like to replace them with 0 and 1. So the 0 is the class of the people who actually survived more than 5 years, and 1 will be the task for people who survived less than 5 years. And why I'm doing that, I would tell you later when we dive deeper into our EDA. So just now, for now, I want to actually replace 1 2 with 0 1. I just want to replace for now. And once I do that, when I can see that df dot, okay, I can copy the code from here. I can say 0 and 1. This is what I want. This is actually what I want. So now let us see the description, data description. So df dot describe. When I use the description, we can see that the age. So you have the minimum, the age. If I can, put a comment here, minimum age is equal to 30. So you can know that this is a class of people who has the minimum age of 30 and maximum age of 83, we can say. So my class of people is aging between 30 and 83. The year is very simple. The year is from 58 to 69. Operation year is between, I can say, between 1958 to 1969. This is the operation year. If you see nodes, there is one important thing when you see nodes. For nodes, range is between 0 and 52. This is the range of nodes. And survival, we all know that survival has the range of 0 and 1. But in nodes, you can see one thing, that the 75th percentile has only 4 nodes. You can see the 75th percentile will have only 4 nodes, while the maximum is 52. So you can see that the distribution is very much rightly skewed. It has like 75 till 75% of the value you have 4, but maximum is 52. So intuitively you can say that the nodes have higher count density between, I can say, 0 and 5, 0 and 4. So I can take 4 as 75. I can write here as the 75th percentile. So from here, we are now slowly getting some ideas about what is happening from the data description. Now we can start with the univariate analysis. So let us understand about univariate analysis. Univariate analysis is what we have actually started doing from the data description, because we have seen the ranges of all these people. So the first thing I would see about survival. The first thing, let us understand about the survival here. What is the survival feature? What it says. The first feature was survival. So in this case, I can simply say that df dot survival dot value counts. It says that you have 224 people who will be living more than 5 years and only 81 people who will be living less than 5 years. And when I convert it into the percentages, I can see that what I can understand that there are only 26, or I can say maximum, like if I round it off to two digits, so maximum there are only 27% people who will be living less than 5 years, which means the data set is imbalanced. Obviously the data set is imbalanced because see, nobody wants to live less, right? Everybody wants to live more. And from this analysis, what I can only figure out that there are many people who is like actually living more than 5 years in the data set, and very few people who are actually living more than less than 5 years. So my major concern is whether this 27, would I be able to actually figure out a lot of insights from only 27% of my data set, so that I can actually make some kind of conclusions for somebody who will be coming and asking me that whether I will be surviving more than or not more than. That is a bigger question. So in this case, the data set is imbalanced. For a building model, if you're building some model, you can, I don't think you would be requiring SMOT here, but yes, you can, if you want, you can use SMOT here for building your models. But I think this can pretty do the job even without using SMOT and all. But still, the data set is imbalanced. Not highly imbalanced, but it is imbalanced. Now, we can just use this information to make a graph, because this is what I'm telling you as a data scientist or data analyst. This is your job to understand from these figures, but maybe the higher management won't be able to understand just by giving figure. They don't have a lot of time. Just joking, but still, it's better to write all these insights, but also if you can make the data, make some plots in order to make somebody understand. So this is count plot. I'm using the Seaborn here. So this is what a survival feature can tell me. Now let us go to the age feature. What I can understand from age. Now let us understand it. This is the age feature. So what insights can I get when I'm actually analyzing age feature? So we have already seen about the minimum and maximum age, but still you can use describe function to actually figure out once more that the minimum age is 30 and the maximum age is 83. This is one insight which we have already got from data description. Now we also want to understand the density of the distribution, like how many people the people who have come for the operation, the people who have got operated at a particular year. So how these are distributed actually. So we can actually say, first of all, I also want to understand how skewed is the distribution. So df.age, skewness is not generally, we will not be able to use any information by the skewness, but you can actually use it while you build a model, because many a times it happens that if you have a Gaussian distribution, the results are better. So there are some techniques which are applied, like transformation or something like that, so that your data can be much more near to the Gaussian distribution rather than just skewed. Here I will use the bin width of 5. You can use 5, 10, whatever you want. and also I want KDE is equal to true. KDE is actually giving me the probability density, this figure or function. So here when I run this code, you can see here that most of this is actually I have taken the width as 5. So you can see what you can conclude from here, that the maximum people who were operated were in the age group of 50 to 55. So you have a fair bit of idea here that people who were operated, the maximum people who were operated were in the age group of 50 to 55. You can try and change the width of the bin width. Suppose I make it 10. So in this case, you can see from 50 to 60. But as and when you try to, take the smaller bin width, you would be able to find out more number of, more details about which were the highest, which age group had the highest, and something like some sort of that information. Suppose I take it from 2.5. So in this case, I can say that people from 50 to 52.5 were the highest age group. But you do not have to go very low in bin width, because what will happen then, the data may try to overfit. You won't be able to get the proper pattern, but you would be like overfitting yourself. Like you would say that the person who is aging 52 will have this kind of a survival. We don't need that particular age. We need some ranges. So in this case, I'll limit it to 5, because 10 will be the information you will get when you have the bin width of 10 will not be that sharp. You might do some errors in, if you have the high bin width. So this is what we get when I am using the age here in this case. Now, I also want to understand few things, like how many, what was the age, like what is the proportion of people. From here I can know that the maximum proportion or the maximum people were of 50 to 55 years of age. But suppose I am doing a CDF and a PDF plot actually. So in this case, if I write SMS dot CDF plot x is equal to age, data is df, and we are trying to use the hue as survival, means we want to highlight our visualization as per who survived and who did not survive. So in this case, I can use, maybe say, suppose for given condition, I don't know currently, I'm just using 50. I'll let you know what is that 50 here, and maybe I'll use this color as black. And here also I can, this is my horizontal line, that was my vertical line, this is my horizontal line. So in this case, let me see the proportion of 50%, and let me write C is equal to color. C is nothing but color. I'm assuming that you all know these codes. It's very simple. You have to do that ECDF, this cumulative probability function here. That plot you have to make with the vertical line with color black and horizontal line with color red. And what is this? Let me show you once I run this code. So here you can see why I have done 50 here. I just wanted to know the proportion. This is the proportion, the percentages, and these are the ages. So here I do not, in 50 I cannot find out anything. But suppose, say I'm changing this to maybe, suppose, let me do 63, for example. What I can say that about people who are, okay, let me do 60. Let me see what 60 gives me. Okay, 60. Okay, yes. So you can say that around 70% of the people were of the age 60. This is 60 years. This is actually the marker which which can help you to locate. So here what you can see, the age is 60, and when you actually see the horizontal line here, it is a kind of more than 75% here. Let me try to make it 80. So in this case, if I use suppose 65, here it cuts, the black line cuts at this point. So if you extend it, it is just above 80. So you can say that around 65%, sorry, 80% of the people were of the age below 65 or below. So what you can get it from here is nearly, or I can say 80% of the people were 65 years or below. However, we know the maximum age is like 83. So I can say that mostly the people were from 65 or below, maximum 80% of the people. Let me see this. I'm just looking what insights I can take out from this. So we can also try to change it also, like later. If I can say not 50, suppose I want to understand how many percentage of people were there who were 50 years or below. So here I can say that around 40% of the people are there. Around here you can see 40%, nearly 40% of the people. So here you can also say one more conclusion, that 40% of the people, and if I want to make it 60, this is 45, I want to make it 60. So let me make it as suppose 55. So you have to do such kind of things so that you would be able to understand it. So 55 is more. What is 50? This is 50. This is 50 around. So it should cut here. So you can actually make it as 52. Yes. So you can say that approx 50% of the people are 52 or below. 52 years of the people were 52 years or below. So this is some kind of conclusion, some kind of things which we can get it from the univariate analysis of age. Okay, now let us analyze the operation here. Now let us analyze the third feature, which is operation year. Many of the people would think that why operation year is very essential to analyze, because it's just a year. But guys, it is very important, because you should know at what particular time the maximum uh, people who survived less than 5 years, because at that particular time it not might be only few things which would be giving them that kind of a disease which led them to survive lesser than 5 years. There might be some changes in the hospital facility, or maybe the doctors were not very much competitive. Anything can be that. So you are not judging anything, you're just trying to just make some analyze some patterns. So operation here is also important. So here in this case, I would like to see the value counts, like at what, how many operations happened and which year. So these are years and these are the counts. Kind of, cannot analyze it properly. So I can say that I can use plot here. Plot kind, let's say bar. Okay, so now it is very clear. So you can see that at 58th year or 1958, there was a highest operation which was done, 58, 64 and 63. The minimum operations were done during 68 and 69. So this is the trend. So here you cannot actually get a lot of insights, but you can say that during after 67 the operations were lesser, like done very less operations were done during these times here. And now there is the question, if you want to know, then you can write why the operations, like it is the work for the management, why they have to think that why the operations were done lesser here, lesser, and the trend of operation is decreasing. So people should know that why the operation, the why the people who were operated reduced each year. Was the doctors not capable enough, or there were higher percentages of the people who were actually surviving lesser than 5 years, as and when they started going to this hospital and getting themselves treated? There are a lot of questions which this plot can show. So this is what the point is. So I don't think that age, the operation here, I can actually go on and analyze it furthermore. But yes, this is what this is about. So let us analyze my fourth feature, which is the lymph nodes. As we know that the range of nodes were from 0 to 52, and the 75% of the nodes have been were only 4. Now let us actually do such kind of things here as well. Let me see the distribution of the nodes also. Here I can say nodes, and I can fix the canvas size here as plt dot figure size. Let me take 12 and 6. So once I see here, you can see the maximum people were having the 0 lymph nodes, then 3, then 1, then 4, then 7, and it has the very decreasing kind of a trend. Only few nodes were important, like I guess till maybe 10, 10 or 13. Only up till this, I think the figure is important. After that, these values are very, very less here. Okay. So this is what a distribution, and as I have said earlier that 75% of the nodes were restricted to 4. So the data is obviously a right skewed data, that at any cost. And you can actually use this also. You can actually check the distribution here as also. You can copy the code from here and you can actually change the nodes age to nodes. You can see here the distribution is very much rightly skewed. It's like at least 3. The skewness is 3. This is not a good sign. This is a kind of very much right skewed. If I increase the bin size, you can see this. And up to 0 to 10, the uh, the the density is much more like relevant. So here I can actually get one very much important insight, that nodes or the density maximum density count for nodes are between is between 0 and 10. This is very much important. So this is what we can take out from the univariate analysis here. Now it is the time for bivariate analysis. Now we have to analyze the data set as per the bivariate analysis. The bivariate analysis, as it says, it is a analysis taking two variables or two features at a time. Two features, bi means two. And gist of this bivariate analysis we have already started up in this plot, actually a CDF plot. So though we were actually taking the age, but we have taken the hue or the coloring, the differentiating color as a survival. So this actually becomes my kind of a bivariate analysis as well, a kind of bivariate analysis. But now we will see how the bivariate analysis can be done. So here we can actually do the analysis between, suppose starting with age and survival. We can do this. Then we can use, suppose, nodes and survival. Then we can do years or year and survival. Year and survival. These are the 3. Then we can do maybe age and nodes. Then we can do year and nodes. Then we can do age and years. These are the maximum combination of the analysis which we can do. We can check the, as there are 4 features, so basically we can use 4C2. It will be kind of a 4C2 analysis, which will be like 12 plots. But since we read age survival or survival age as 1, we can do the 6 feature plots and we can analyze each one of them. There will be some plots which will not give you any insight, so you don't have to worry about that. You can just leave it. So starting from the age and survival, let us do the box plot here. So here we can use SNS dot box plot, where you can put x is equal to survival, x is equal to survival, y equal to age, and sorry and data is equal to df. Though we have actually seen the age survival thing from the ECDF plot as well, but let us see this also. So here we can see the box plot. You can see there are no outliers first of all, and secondly we can see that this is the mean, or if you can say the median here in this case 50 percentile is kind of same only, like the maximum a maximum age is more for someone who has not survived above 5 years. But this is, it just gives me a hint that the people of higher age tend to die, or I can say that the people of higher age or age, so this is 25 percentile, 50 percentile, and 75 percentile. So you can say that the people above, maybe above it, above 75 or maybe 77, or you can say a kind of, this is what value, what could be this value, kind of 76, 77, a kind of people after age 77 or 76. So to keep this simple, so I can say people with age greater than say 75 will have, maybe say, or if you can increase this to maybe 77, greater than 77, will actually live lesser than 5 years. This is a kind of a actually live lesser than 5 years, and the probability you can say is, probability is like 99% probability, 99% probability you can say, because from this plot, see, nothing, I'm not talking about the sheer number, I'm just speaking about the fact that you can see the maximum value ends nearly at 77, 78, kind of that value, and above that all people will actually kind of dying. So we can say that our maximum, like it will be kind of maximum possibility that people after age 77 will live lesser than 5 years after operation. But if you can see here, this value is kind of 1. So this value is kind of between 30 to 40, and you can say 35. So you can say people, or you can say like 34 or 33. So you can also figure out from this that this whisker is actually little less than 35. This is not actually the mid, but little less than 35. So you can say that concludely that people with age lesser than 35 will actually live more than 5 years. And this is also certain 99% with probability, because I can say this. See, we are not concluding anything here. I cannot, as per the data set, I can say that it's 100% probability, because I don't see these values here. But if you want to conclude, you can say this. So it is actually, legally I should not write any probability thing or not, but you can say this conclusion. So let me like erase it. I don't want the wrong information to propagate. I just want you to understand that these are the ranges which you can actually find from the box plot, And as per this data, the probability is 100%. But the data is very small here in this case. Now, I want to understand also with, like, I want to actually reconfirm this thing actually in this case also. So let me use a plot which is called a facet grid. So let me tell you what it will do. So it will actually help me to identify the proportion or the percentages of survival as per age. So here I can write survival. Then I can use height as 6, 7. So height is like you can choose whatever you want, and I want to map it with the his plot actually. His plot. Age, and let me take, because I here also for age I have taken bin width as 5 kind of. So let me use bin width of 5 here. Bins 5. KD is equal to true. KD is the kernel density which it will show. And also I want to add the legend. Now let us label. So plt dot x label. This is the label. So the first label shall be age. The second will be plt dot y label. Here I can say percentage of survival. And here I can, if you want to give a title, you can give it, or if you don't, if you want to check it, you can check it. I'm just trying to give it a title to put it more presentable. That is PDF for age count. Size, I will write around 12. And then I can tell plt dot show. Once I run this code, I can see one particular thing here. This is one is the people who have survived lesser than 5 years, and I can see that between, this is bin width of 5, right? Let us change it to 10. Why I'm changing it to 10? Because you don't see, there are two histograms, and actually these are somewhat differing. I just want to check whether they can overlap for me to get the answer. So here this seat is overlapping actually in this case. So I can say that around 40, so this is the starting point of this histogram here. So it is not actually 45, lesser than that, I mean 43 kind of, and this is 55. Let us keep the value 45 to, I can say that 43 to 53 kind of thing you can actually keep. This is the width here. So here this is the width, which is like, this is not equal to for 55 here because it's not actually at mid. You can kind of say that between 43 to 53 age group, the people actually are much. The count of people who are surviving lesser than 5 years are actually between 43 to 53 age group. So you can actually say one thing here from here, that so this is 40, this is 50, and if I change this width to 5, I just want to properly see this, and let me change the size to 15. So here you can see this is 50 here, this is 50, and 50, and this is 50, and this is 60. So it is kind of in midst. This is lesser than 55, and this is 40 and this is 50, so 45 should be here. So the maximum will be like 44 to 45. This will be a kind of age group. So you can see tell from here that percentages, maximum percentage of people living lesser than 5 years, can say 45 to 55, let us put it this way, are between, I was trying to get some particular figure but not actually, you can see the range is between 45 to 55, between 45 to 55. This is what I can actually conclude from it. Maximum people living lesser than 5 years are between 45 to 55. Now one more thing which I want you to do, but actually that will be a kind of particularly getting much deeper into data, which is not actually required, but it can give you certain insights about this data, that you have to do the group by function, df dot group by age, and here I will tell you why I had used the value counts of 0 and 1 for survival. And I want to sort this. Let me do this. Oh, sorry. Let me just do this. So here you can see that the 53 people of age 53 is having the maximum, like 6 people are positively declared. Like this is sorted from ascending order. I'll just have to do ascending is equal to false. So here I can see 53 people have been served. So what I have done this here is I have grouped the data set by the age, and then I have taken the sum of survival. Why I have taken the sum of survival? Because whatever ones will be there, that will be added up and the zeros will be eliminated. So for 53, I am having the sum of 6. So that means that 6 people will live lesser than 5 years who are in the age of 53. 46, 43, 65, 54. The range which I have seen here is from 45 to 55. There are maximum people between that. And if you see this range from here, 41, 48, 43, 61, 47, if you see, there will be more number between 45 to 55 here in this case. And also you can see you can also uh, take out the percentages also. Let me show you how. So in this case, what you just need to do is just copy it here. These are some detailed analysis which is most often not required because it won't give you the pattern actually, but you can actually get more confident about your analysis part. When I use this, so these are the people who, so 50, there are 14 people of age 52. Now let me see 53. So because here the highest is 53, so 6, and here is 53 is 11. So 11, 6 out of 11. It is more than 50% chance that people who are 50, who is 53-year-old will live lesser than 5 years. But again, this is just, I don't want the number, I just want the number bracket because because the data set is small. So in this case, if you see that, okay, 38 you have one people who will be living lesser than 5 years, and you can see how many people are there in 38. If you can figure out, so 38 there are 10 people, so 1 out of 10 the probability is less. But okay, let us go to 39. So 39, how many people are actually present with the age of 39? We have 6 people, so 1 out of 6, again that is okay. Now let us see 59. Why I'm going from downwards, because when you have small data sets, no, so if that would be the age group, in that particular age, like 59 or 58, there would be only one people, and one people will be positively detected that he will not live, he will live lesser than 5 years. That doesn't mean that all people for the same age group will actually live lesser than 5 years. So 59 is 1. So you can see that what is the 59. 59 is 8. Again, that is okay. So just have to see. I'm just trying to figure out if that is a kind of thing which I get here. 59 is not there. 83 is there. 83 is 1. See, 83 is 1 here. So there is only one person with the age of 83, and that particular person unfortunately does not live more than actually 5 years. So you cannot actually say blindfoldly that 83, the person with the 83 age will eventually die, though the analysis also says that people who are like more than 77 with age will actually live lesser than 5 years. That's one thing. So let us see some people with the age less than like 83. This is 83 after 7. So let us see someone with an age of 63. Let me see what the people with the age 63 here. There are 8 people. Okay. And similarly, if you go to 67, how many people are there in the 67? There are 6 people in 67, and there are 2 people. So around 2 by 3, 33%. So in this case, you can actually get to know the percentages. But what I am manually doing here, whatever I am manually doing here, that can be actually done from this plot. I am trying to figure out. So I am trying to prove this plot from this. But when the data set is bigger, you may not be able to do it actually. So this actually can give you much better clarity that, okay, from 45 to 55, there are much. So from 45 to 55, how many people are there here? So you can see you have 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9. So 9, 10, 11. So if you see out of, these are numbers like 20 numbers, you can say 11 or 12 people are from between this age bracket. So this age bracket is much more like having higher potential of being kind of the people who will live lesser than 5 years. You can also check, you can actually you change the bins, so you can actually figure out here. If I increase the bins more, the data will be much more clearly zoomed up, that how many people. So here you can see that the more number of people are between lesser than 50 and 45 to around 2 3, this, but this is like the data set is small, so people will be here less. So in this case, I'm trying to do a zoom it much more so that I can get from actually 45 to 55, but it is lesser than 45. So you can say around 43, or around, say, let's say 43 to maybe 53. This kind of thing you can actually figure out from this kind of a plot. So this you have got. Now there is one more thing which you can actually do here, which is called a which is called a joint plot. So with a joint plot also you can actually see this. So I just want you to take a glimpse of what it can show. So guys, these all things are very much important when you are actually analyzing the pattern and everything. So here you can see I can write age, then y as survival, sorry, data is equal to df age, and suppose, let me do nodes here, but this is a kind of 3 variable analysis here, but it's okay. I just want you to see the glimpse. I want to take the hue as survival, and I want to take kind as KDE, and you can have the title as well. What can be the title? Age and nodes PDF by survival. Then you can simply say plt.show. When I do this, you can see the distribution. This is the joint. Again, this is a 3 variable analysis. So you can actually do it after bivariate, but I'm just including as per the age and survival. So here we have seen age and survival, and I am doing age, nodes, and survival as well. This is the second kind of plot which I'm showing. So here what you can identify is that people with, this is the maximum here, maximum node, which is 0. This is the maximum, 0. And here in this case, the maximum comes out to be between this one. So blue is the people who have survived more than 5 years, and Orange is the one who have survived less than 5 years. So you have to see the orange one. So I can actually use the bigger figure size. Comma 6. Nothing changed as such. Okay, just leave it. Let me see here only that this is the peak. Actually, this is the peak, and when you see at this particular peak, the node is between 0 and approximately 5, the maximum. And here you can see the peak rises till here. The peak is here approx. It is kind of 50. So you can say the people with age 50 around the bracket. If you see this the highest age bracket, you can see the age bracket is around, this is 40, this is 50. So you can say around 43 to around 53, the same kind of a peak which you can see here. So you can say that the age between 43 to 53 and we'll come to nodes also, but from here you can see the range of nodes is like from 0, kind of, this is 0 and this is 10. So from 0 it is like till 10 it is kind of a okay kind of a thing. So the range of nodes, we need further analysis to find out the range of nodes, but from here we can analyze one important thing, that from 0 to 10 the orange line, the percentages, but you have to also understand about the blue line as well, because the percentages may be less, but from after 10 you can see the blue and orange lines are like flowing together. So the percentages of orange line or the survival of people above below 5 years is higher in this case. So the people tend to die in the 5 years after operation in this range, but we will actually see this when we just analyze about the nodes here. So before this, let us actually see what we have done. So here we have come to a conclusion that maximum percent of people are living lesser than 5 years are between 43 to 53. Here from 30 to around 33 years, so that you can actually also figure out from this case, just for the proof's sake, 30 to 30 years. So here you can say 30, 31, 32, around 35, 33, 36. These people are about, but here you can see how many people have actually got 43 in the 30s. How many are this? 34 is here. 34 is here. So I cannot take the range of 34 here. So I can say that this is between 30 to 33 kind of. So I can say maximum percent of people between, or I can say people between directly. I will not say maximum, because as per the data set 100% people are surviving, or people between 30 to 33 years old are living more than 5 years. This is one of the thing. Now this is Now here what we have concluded from the age as per the univariate analysis, as we have seen here, the maximum people who are operated were in this range of age, right? This is what we have done. And okay, somewhere we had shown that uh, people after age of 77, okay, here we had shown that people with age 77 will actually live lesser than 5 years. So this is also very true, because so I'm proofreading with different kinds of plots, because this will actually, age 77 will live less than 5 years, because here you can see this is the gap, and here 100% of the people are dying here. And the same thing you can actually see from here, from the age part, that you can see 83 and 78, one people are dying. So here in this case I will tell that, and now this is my proved conversion or proved analysis from the age and survival. So here I will try to highlight it furthermore. I will use this. I will try to highlight this. This is the final conclusion from the age and survival part. Now I'm trying to understand the nodes as well. So here I can see, if I see the box plot for the nodes and survival, I can see here that this is a kind of a very good features. The nodes are one of the very important feature here, because you can actually demarcate between these two. If I say remove these outliers, it will be very easy for me to say that people who have the nodes above maybe 7, say this point is 7, will actually live less than 5 years, will actually live less than 5 years, people who have nodes more than 7. But we don't know about we are not a domain expert, and we don't know whether this outlier should be treated or not. So I'm leaving it as it is, because it is very important for you all to understand if the outlier should be removed or not. And from this case, I don't think so it should be removed, because we are no one to actually figure out, or it will you need a domain expert to know whether these many nodes are possible or not. So I'm just keeping it for now, but let us copy this code here, and we can try to figure out the percentages distribution of this nodes. I won't keep the kernel density here. I will tell you why. And this is the nodes, percentages per PDF for nodes. So here when I run this, I did not do that, because you see from this joint plot I have already figured out this. Here there is a certain overlap, so KD would have actually made it little bit difficult to visualize. But here you can see before 10, this is a 10, this is kind of you can say 7 or 8. This is this part here. Bins, suppose I change bins to 10. So here you can say 0, 5, 10. The percentages increase heavily after 10. You see here, the people who has node more than 10, in this case, the higher chance of that they will live less than 5 years. but I'll just put bins as 5 here. Up to after 10, this is like, this is very difficult to calculate, but we can say one thing: after 10, this percentage is very high. And from here you can say also one thing, that people after like node 7, after exceeding 7 or 10 nodes, the higher chances that they will be, because this is the outlier here and this is the density plot, and people, the density here, the density is much more than here. So you can say one particular thing, that the people with nodes maybe above 7, or let me see, say 10 to 52, because the maximum is 52, will will have the max, or I can say that will live lesser than 5 years. And we can try to figure this out by the group by function as well. So I would like to say group by nodes survival dot sum. Remember, because of this function only I had replaced the value of 1 and 2 from 0 and 1, because I wanted the person who will be living lesser than 5 years, they should be 1, so that if I sum them up I could know that how many persons are there. Sum dot sort values ascending equal to false. So there are 27 people, but let me tell you what, df dot nodes dot value counts dot sort values ascending equal to false. In this case, you can see the 0 has 176 people here, and 27 out of 176 is not a big percentage, trust me. Now 1 is 20. What is 1? 5. So 5 out of 20, which is a kind of, 5 out of 20 is 25%. So one people have, you can actually divide it. What is 27 divided by 5? Sorry, 27 divided by 176, right? 176. If I run this, around 15%. So you can say people with have node 0 have around 15% chance of dying before 5 years. One will have 25 years of chance. Similarly, if you see 3 nodes and 20, 3 is how many you have? 3 is 7, and this is 20. So 7 divided by 20. So 35% chance. So I will write for 2, but for 3 you have 35% of chance that you will survive, or I mean say you will survive lesser than 5 years. For value 2, you don't have 2 anywhere, but okay. When there is no value as 2, you can surely say that it will be incrementing. Now what you would say, 1 3, then you have 4 as 3, 4 as 13. 3 out of 13. 3 out of 13 is 23%. So 4 has around 23% of survival. I'm trying to just take few values. 5 is 4. 5 is 4. What is 4 as 3? 4 was 3 and 5 was 4. So 5, how many of them are there? 5 is 6. So 4 out of 6, I guess it will be much more. Around 67% people will have this. 67% people will, with 5 nodes, sorry, 5 people with 5 nodes will have 67% of chance to 67% chance that they will die before 5 years. Now let us see quickly. Let us see. This is 7, 6, 7, 8. 6, 7, 8 are all 7, 7, 7. Sorry, not here. This is 6 is 3, 7 is 2. 6 is 3, 7 is 3. 6 is 3, 6 is 3. What is 6 here? 42%. So see the value which is increasing, 43% nearly. So this is how you can do. Just you can check directly. What is 7, 7 here? 7 is 2. 7 is 2 here. And what is it? 7 is 7. So 2 out of 7. 7, it is 29%. What is 8? 7. Sorry, here. 8 is 2. And here 8 is 7. 2 out of 7. So 8 is also 29%. 9 is 4. And here 9 is 6. 4 out of 6, which is 67%. 9 is 67%. And finally, I'm just trying to do till 10. 10 is 3. 1 out of 3, which is a kind of 33%. So like this you can actually do. I'm trying to just do all these things just in order to tell you how you can actually approach. Somewhat proof you can actually see. But after that, if you can see, till 10 you have certain point, like 5 is dangerous, like 5, you can say 5 and 9 are some dangerous numbers. But if you have this overall thing, so overall average will come out to be somewhat between around 30 or 40. But after that, if you can see, the percentages will increase a lot. Suppose I say 13 is 4 here and 13 is 5 here. You can see the percentages. 4 out of 5, which is 80%. When I say about 13, the probability increases to 80%. Can you just believe it? Now, if I go above 13, if I say go above 13, I go to 23. 23 is 3 here and 23 is 3. If I simply randomly choose 23, I get 100% of the probability. So I can say that after 10, people will definitely, like, there is high chances that they are going not to, they will not survive. So this is a kind of a proved statement here of what I have proved from the analysis here and from this part. So here I can say, I can actually highlight this as well. This is also a very important thing which we have figured out. So now when age is done, and nodes are done. Let us go and find out about the operation. I can just mark this so that you can all understand about this. Now operation, year, operation year. So for year also, this is a very important plot because year is all numbers. So box plot, I don't think so will actually make a lot of sense here. So I can just take this as a year and this as a year and PDF of year count. I'll just put KD is equal to 2 in this case. Bins, should I decrease the bins or increase the bins? I think I should increase the bins here. So here you can see the maximum. This is 64 to 66. This is the maximum here. The percentages is like higher, but you know the deaths have happened here is higher, but this is also higher in this case. But here this is the part, this is this, like it from, you can say what should be done. Let me take it as 8. Yeah, I think this can be useful here. So this is 1 year, which I would say that it is between 64, this is 65, 66, 65, 66. Because see, this is like more than 50% here, which it is showing. Orange is like 50% of this blue here in this case. This has the higher thing. This is also like 58 to, these all years have seen some increase actually. If you see, these all years have seen some increase. So you can say that these are actually some. Now let us dissect this further. So what I can do, df dot group by survival year dot value counts dot unstack. Once you do this, you can see how many operations have been done and how many, like this is 12 out of 24, 50%. So if you see, the total is 36. 1/3 people have died in this case. What is the percentage? This is 1/3. This is 50% people, 59. Here it is much lesser. Here also lesser. Here also kind of lesser. Here also it's 8 out of 30. So kind of lesser only. This is 65. Deadly. This is deadly here. 65. This is also 69 is deadly. 3 out of, so you can see which all years are somewhat, you know, some. So if somebody comes with a year of 65, maximum percentage of the people will, you know, just are actually dying there. 13 divided by 15, how many? 87% of people. So if I can say 1965, not it, 13 at 15 plus, this is 28. 46% of the people have died here in 1965. How much for this? In 19, sorry, 1958, kind of 33% people have died. 9 out of 20. 9 out of 20. Around 45 people have died in 1959. 45% people have actually died. And here these all will be less here. Which all things should be seen? This 65 one is major. This one is major. So I think that this is the actual range here, because here also, this is 4 out of 11. How much is 4 out of 11? Around 36%. So overall, if you can see, the maximum is around 45% here. So you can say that people who has around who have been operated in around 65, 66. 66 also is 6 out of 28 is how much? 6 out of 28, 21%. You can say that nearly 65, 66 and around 58, 59. The operations there were people around 40% which who were dying during this time. So you can say around, this is 21.4%. What is the average? 21 and 46. 21 plus 46 is 67, divided by 2 is around 33.3. So around, you can say that this, you can actually write it 33% people died before 5 years. When operated between 1965 66. Such kind of things, though this is not a very, kind of a thing which is very much essential, but okay, this thing has to be taken into consideration for one particular thing. So this is also very important case to consider. Also, you can actually use you can also change this to dist plot and see, because the vertical lines will be, go. So here you can see the maximum is 65. So maximum is 65, which is a 46%. You can also highlight this. Maximum is this part. So this you can actually convert it into heading. 46%. So this is a very good information which can be used. This is what a very, so by this you can see how importantly we did bivariate analysis to come out to conclude these all points, these 3 points. Then you have this 2 points, nodes importance and all these things, and then year also. Now it's that when we have gotten so far, let us also, before going there, I would also like to do the joint plot analysis as well, like this, because the age, nodes and survival was done. I would like to see the year as well. So Here I would like to see the age and year. See, age and year. So this is the peak here, kind of peak here, around 65. This is also giving you the same thing. So you should have the combination, basically the age, the year, the operation year, something like this. Also you can use this. We have used age and nodes, age and years, right? What else is pending? I guess these two joint plots can only be possible here. So this is also proving the same thing what we have opted. Now let us go and see some multivariate analysis. Basically, multivariate analysis is generally like what I have actually used is just for basically the correlation. Howsoever, since data science and everything, these all are field where you have to learn it every day. If somebody has some kind of a different kind of interpretation of a multivariate plot, please actually help me out in this. So first I'm trying to make a heat map here with a figure size. I'm just whatever figure size I was keeping, I will just be using that. But let's say I'll just put 7 and 7. Let's see. And you just need to make the pivot table here, which is df dot core, and then you can use sns dot heat map, then you can use this pivot table here, then you can use stick labels, core dot columns, white tick labels, the same. A note, I need to see the correlation, right? Just have to see that. And this is done. So this is this is black, and so you can actually change it to whatever color you want. If I say want C map as maybe blues, so the color will be much more interesting. What is the problem? Oh, now see, let us increase this to 10 and 7. So you can see one thing, nodes is a very important feature with 29%. Nodes and survival are very much correlated, 29%. This is not a very big correlation, that is avoidable, that is not an issue, but nodes is actually affecting survival a lot in full. So year and survival, you can see this is negatively correlated, so you won't be able to find out any important thing. This is also very very low correlations. This is very very low correlation. The only particular correlation which you get is nodes and survival. So nodes and survival are somewhat correlated. You can use this, the final conclusion. Nodes and survival are correlated by 29%, which is the highest. That's it. So this is the end of your EDA. I don't think so it was quite exhaustive, but I have taken this small data set because you can actually be able to gather and actually understand the approach which we have. And now the final thing, this is the agenda. If given a patient with some particular age during operation, year of operation, number of lymph nodes detected, we have to predict whether they will live less than 5 years or more than 5 years. So by this whole thing, I can say that if somebody who is coming between the age of 30 to 33, maximum I will tell that they will be living more than 5 years. If they are coming between 43 to 53 or nearby these values, I would say that they have to be careful. They might not live. People with age more than 77, I'll definitely say that, dude, you have lesser chances to survive. Also, if people with nodes bigger greater than 10 to like in the range of 10 to 52, if they will have such kind of high lymph nodes, definitely I would recommend that they might have to live lesser than 5 years. So please go ahead and get some prerequisites done so that some other operations or something can be done so that you can actually live more. So these are very important things which we have seen here. Also, we can say if somebody coming and he's telling that, okay, dude, I have got operated in 1960 this year, last year 1965, what is the chance that I might survive? I would say that, dude, for around 46% of the operations in 1965, 46% people actually lived lesser than 5 years during the 1965 operations. So yes, this is not a big probability, but yes, you have to be careful. So these are some basic conclusions which is very important, and I would definitely say notes are very important here. So for me, somebody who is like even suppose in the node of, suppose somebody who is coming to me who has the node of around maybe say 2 3 lesser than 10, and age, even the age is this age is in this bracket only. But since I know nodes, if you talk about feature importance, node is very important here because node is affecting survival a lot. So I would definitely say, dude, if you have nodes lesser than 10, but even then you are in the age bracket of 43 to 53, which saw the maximum deaths before 5, I would definitely take a bet on you that you might live more than 5 years. So guys, I hope you are understanding this properly. There are few manual calculations which I did, but just in order to show you how you can how you can analyze the data. I am not telling that you just have to go and analyze 1 lakh rows data set in such a way, because often when you have a lot of data, the results are quite distinctively viewed when you would actually see it, because you will have a lot of chunks of the data accumulated. It won't need actually such manual calculations, but even if you need, you can use such manual calculations to prove your work. Actually, 1 or 2 manual calculations is better. So this is how this EDA has been done, and I hope you actually learned a lot from it. And if you have certain idea which is like missed by me or my team, please write to us so that we can actually take care about this from the next EDA activity. So that's it for the video, guys. Thank you.